Alrighty. So we are starting the
Although
recorder.
apparently they're flexible because his feet grew with it.
Alrighty. So I'm going to get started. This is the very last lecture of this class. Okay, so we are at the end of the semester here. 1 week from today is our final exam. The final exam starts at 8 o'clock, not 7 o'clock. It starts at 8 o'clock. In fact, you can switch back to the browser. So this is where you find the exam schedule for all of your classes. And I do not think that professors are supposed to mess around with changing this time, because if I change the time of this class, it can potentially cause a conflict with your other classes. This is scheduled so that there will be no conflicts between classes, unless you have classes that are overlapping to begin with because of a petition. Okay. So according to this, our exam time, our final exam time is next Tuesday on the 21st from 8 to 10 p.m. and it's going to be a paper test, just like exam 1 and exam 2, and it'll be done here. Okay, and just like with exam 1 and exam 2, it is open book and open notes. I was about to say open source, but that's not.
Open source? Open computer? Open computer?
Not Creative Commons either. So anyway, it's going to be open book, open notes, just like with the previous 2 exams. And then at the end of today, what I can do is I can archive every single folder, for each class, and roll everything into one zip file, post it onto Moodle. Then you have all the files that that I worked on for this entire semester, all in one single zip file. I think that might be helpful. You can just ignore it if you don't want it. Yep.
You were saying this exam is going to be more like, unlike the first one, more like the second one, where you're going to be doing a lot of actual code stuff.
But I also have to design it so that I don't have to use 6 hours to grade the entire thing.
But the final exam. One person. So we're going to be studying.
It's going to be the last exam I'll ever grade because I'll be dead. That's final.
Yeah, just write all A's on them, all right? Make it easy on yourself.
So is it going to be multiple choice? Something?
No. But what I will do is I will make it so that it's easy on me, but not so easy on you guys.
That's not good.
Just do A.
No, but I do have plans, like a debugging session, so I will give you the assembly code, the C code, the assembly code, and then you'll basically have to go through the instructions and find out why it's not working. So you have to kind of indicate why it's not working and how to fix it. There'll be like obvious problems like addressing nodes, those are the really obvious ones, or invalid operand, not the operands, invalid mnemonics. Okay, so those will be the easy ones to spot. Like you have a move W on one side, and then on the other side you have a %EAX. Okay, that will be obvious. Or EAX without % symbol. That's kind of obvious too. Just kind of syntax type of thing. But there will be other things too, like you're supposed to dereference, but it's not dereferencing, or it's supposed to get the address of something, but it's but I'm passing the content or the value of something. So the homework assignment that you have, that you are doing until it's due next Tuesday, is going to be helpful. Okay, just being able to finish this homework assignment is going to be, that's good practice for studying for this test already. Because the very same material that you need to get the homework assignment done a lot of that is going to be in the final exam. So as you are doing your homework assignment and you say, oh, I need to get a better understanding of something, and you're jotting down some notes, that is good material to bring to the exam as well. So doing the homework is getting ready for the exam. Yep.
Can we actually print out our homework assignments and use that as
Absolutely. Okay. Absolutely. In fact, I will give you every single file that I worked on in this class. At the end of today, I'll just upload it. You can select and print whatever you want. You don't have to print everything because that will be like a big pile of paper. It's hard to dig through. So you just have to pick the ones that you think are more important to you. And you can also kind of index it too, like use post-its to kind of indicate, okay, this is on this particular topic, and so on. Okay. So are there any questions about the time and place of the final exam? Basically, it's just a little bit longer than our exam 1 and exam 2, but pretty much the same in nature, except instead of having you guys to write code in freehand, which was very hard to do to grade, it's going to be more like debugging, and questions like that. All right. Any questions? No questions? Okay. If there are no questions, I'm going to go over a practice exam for you guys, with you guys, and that's what we were at here. Okay, let me go back to my. So this is coming from last year's exam. Here we have a program. This is the part that is supposed to be implemented in assembly. Let me bump up the font size. It's really hard to read when you're far away. So use terminal. Where's terminal? Well, mono works too. There we go. Okay, that's big enough. So this is the subroutine that we're supposed to implement, and then the other file contains the actual implementation. So if I double click read nums.s, it's empty. So in this particular homework assignment, you're supposed to implement this particular subroutine. I'll go ahead and implement it, and I think this will give you a little bit of clue of how to do the homework assignment too. Let me just do one thing here. Let me just go ahead and decompress the whole thing so we can look at each question easily that way. So, decompress to base folder. There we go. Now I can go back and use VI. Oops. It's a folder. All right, so this is the C code, and there's only really one line to implement, but you do have to indicate the displacement to the correct parameters. So let's go ahead and just implement this one single subroutine. I will do this, so I can actually look at both programs side by side. Do you guys want it up and down or side by side? Side by side? Okay, we can do that too. It's uppercase O instead of lowercase o for side by side. All right. So since we're implementing readnum, let me turn on syntax highlighting doesn't work too well because I think it makes it too dim. So this is just the way we're going to do it. Okay, the first thing I always do is to spell out the displacements to different items on the stack. And this just means, I know some people do not really think that old EBP needs to be tracked, but I always want to remind myself where everything is located. So old EBP gets a 0 because EBP points to its own old value on the stack. The next one up is the return address. That's old EBP plus 4. And then we have our parameters. The first parameter is the one at the lower address because it's pushed last. So in this case, it is str. Is return address plus 4 because the return address itself has 4 bytes. And then the last one is pint. It is a pointer. String is str is a pointer. So in this case, it is str plus 4. That's how we find parameter pint. Okay. So are there any questions at this point about the calculation or the definition of the displacements to different items on the stack? There are no local variables in this case. So if I want to be universal, I can always do something like this. Okay, if I want to have my actual subroutine to be more universal, I can just say last local var is 0 because I don't need to do any type of allocation here. In that case, it's nice because I can just use exactly the same entry code and the exit code for every subroutine that I define. So push EBP to save the old value of EBP before I change it to become the frame pointer for this particular invocation. Note what I said. It becomes the frame pointer for this particular invocation, not for this particular subroutine, because in recursion, the same function has multiple instances or multiple invocations. So this is for this particular invocation, because it's runtime dependent. And then the other thing that I always do is I always also make sure that I do exactly the opposite at the end of the subroutine. And this one is not required, okay? But the nice thing about this is now I don't have to worry. I can have exactly the same 3 lines for the entry code and exactly the same 3 lines for exit code for every subroutine that I define. And when there are no local variables, I'm just wasting the add-L instruction, but I won't forget about it when I do need it. Are there any questions about the structure of the program right now? I'm just dealing with the entry code and also the exit code. I'm not dealing with anything in between just yet. All right, so once we have all of this stuff done, then we can go ahead and actually try to implement whatever is in between. When you look at the C code, there's only one statement here, okay? But the statement has a few things to do. First of all, it has to invoke scanf. Now, I don't really even care about how scanf gets its job done. I just need to push the parameters on the stack, call, clean up the stack, and that's all I need to do in assembly. In this case, pint is the first one that I need to push on the stack. The big question is, am I pushing pint itself on the stack, or am I pushing what pint points to on the stack, or am I pushing the address of pint on the stack? I'm just pushing pint itself on the stack. So whatever was passed to me, I'm just passing it along in this case. Okay? If it is the content, if it's whatever pint is pointing to, you will see an asterisk for dereferencing. If it is the address of pint, you will see an ampersand to mean the address of. In this case, you're not seeing either one, so that means it is just pint itself, which makes the push instruction really easy because it's just push pint open paren evp close paren, and that will do it. Because that's exactly what is pushed on the stack, as my own parameter. I'm just pushing the same thing back on the stack so that scanf has access to it. And the str is the same thing. The format string is going to be the same thing. Push long, str, evp, just like that. Okay. And then I can call the subroutine. Just call scanf, and then I should deallocate from the stack, even though it's not 100% necessary. And there's one more thing to do. What about that return thing? I'm supposed to return the value that is returned to me by scanf. How do we return values like that in C? EAX. And what am I supposed to do to return to my own caller? Well, if you want to, to emphasize the fact that it is in EAX, you can always have an instruction like this. It was passed to me from EAX, and I'm passing it along by EAX. That instruction is not wrong, it's just not necessary. Okay, but it is helpful in this case to remind ourselves that EAX contains the return value from scanf, and I'm just passing it along to my own caller. So I'm not forgetting that I'm supposed to return a value, I'm just passing it along. But obviously it is not needed because it doesn't really do anything that is useful. Are we doing okay so far with this particular program? Q1. This is question number 1 in 1 year's exam. All right. So if this is okay, I'm going to move on. Once again, there are multiple things that are not 100% necessary. Like this one here is not necessary. This one here is definitely not necessary. This one here is not necessary, but if people miss this one, I will take points off. Okay, because remembering to clean up the stack is actually important. All right.
But aren't you already cleaning up the stack by just
But you should clean it up as soon as you are done with that portion of the stack. In other words, those 8 bytes have no values whatsoever after the subroutine call.
So if you remove the move long line and the add long line, which aren't necessary, then your very next instruction after the call is to reclaim the stack space.
Right.
So
it works in this
in
this particular case. It doesn't seem necessary because there are no additional code after scanf. But in general, you might have additional code after scanf, or maybe scanf is stuck in a loop. So if it is stuck in the loop and you're not deallocating for every time you use scanf, you can end up chewing up a good portion of the stack because of that.
So you would take off even if it doesn't make a difference?
That is correct, because it is the structure of the code that matters. Okay, you use it, you allocate stuff on the stack, you make the call, but as soon as that portion of the stack is not useful to you, you should deallocate it.
It's slower, right?
It makes it a little bit slower, but it is the practice that is
It
important.
avoids accidental memory leaks.
Or if you change the program and later on add a loop on top of scanf, if you have this code already in, then you don't have to worry about it because it's already there. Okay? So in terms of execution, yes, the program will still run the same way, but in terms of concept, it is an important step that you should do. You allocate, you deallocate. Is that okay?
If this makes sense, it's like telling a nuclear waste energy production that they need to keep their nuclear waste out of the ocean. They're going to say why the oceans
I
are clean.
understand the concepts and why you do it. It just seems to me that when you write an assembler, your goal is to keep the program small and fast, because otherwise you'd write in C and avoid these possible mistakes.
Well, but strictly speaking, I don't even have to set up EBP because I can just get everything off of ESP. So it's not really whether it works or not. It is whether you can demonstrate that you understand these concepts or not. Okay, you had a question.
Would you dock as points if we instead just popped a couple things off? We just popped a couple things off to restore the stack. Would you dock as points?
So instead of using add
$8,
$8, you use pop.
Two pops.
If it accomplishes the same thing, it will be fine.
Okay.
I'm not looking for efficiency in this class. I'm
Alright.
looking for, concept-wise, do you understand that you have something on the stack that you don't need right now? So you have to deallocate it. You have to keep the stack balanced. Okay. Any other questions about this? No questions? All right. Let's go ahead and move on to the next one. Question number 2. All right, question number 2 is one of those things where you actually have different nodes and stuff like that. So we'll go ahead and take a look at main.c first. Main.c looks like this, and you're supposed to implement this particular subroutine. You are passed or you're given a pointer to a struct node, kind of like some of the subroutines in your current homework assignment. And you are supposed to print the buffer portion as a string using printf. Okay, so that's what you're supposed to do, what you're supposed to implement. And in this case, since this particular exam was done in the lab, in other words, people were actually writing programs in the lab, in order to take this exam. So that's why, it's all practical, and that's why the make file is already here and everything is set up to go. But you can also take a look at node struct.c, and that one has to be finished first. But we'll just go ahead and focus on that particular subroutine. So we'll go ahead and look at main.c and f.uppercase s side by side. Okay. So basically the same thing. I can probably just copy and paste from the other file, but I'm just gonna. This is easy enough. And then we have only one parameter in this case. Pn is the only parameter. Return address plus 4. So if I make a mistake here and do all these calculations incorrectly, it will directly impact the program because you won't be able to get to the parameter that you're supposed to get to. So you got to be careful, about these definitions. Okay, so now that we are supposed to get to Pn, I'll do the rest here. Local var last, local var is 0. So once again, I'm just doing this so I can reuse the same code, the entry code and exit code for every single subroutine that I write. Push L EBP, move L EBP to ESP, and add L last local var to ESP. When I exit, I'll do exactly the opposite. Move ESP back to E. Oops, flip the direction, didn't I? move ESP to EBP, and then the other one is from EBP back to ESP. That will make a good question right there. Flipping the direction of the move, for the entry code and the exit code, because to your eyes, they are still the same two registers, but the direction is opposite. Okay, and that would just mess up everything.
That would
Screw
just
up
be
the entire
diabolical if you did that.
Screw up the
That would
entire
be
stack.
diabolical if you did that, because most people are just gonna work past it.
But if you think about it, how would your program run with those two registers flipped? Okay, let's just think about it. Okay, this is a good time to kind of stop and think about it. If you move if you move EBP to ESP as the second instruction in this particular program, you are forcing the current subroutine to use the call frame of the caller, right? Because EBP is most likely set up as a frame pointer of the caller of this particular subroutine, especially because it's coming from a C subroutine, and C always does it consistently using EBP as a frame pointer. So you'll be looking at things from the perspective of the caller. In this case, the caller is main itself, and main actually has multiple parameters already predefined. In other words, you have ARGC, the number of arguments, and then ARGV, which is a pointer to const char, and those are the parameters given on the command line. So if you flip the order, then you won't be getting this particular parameter. You'll be getting a parameter that was intended for main itself. So the first thing you would notice is in your own subroutine, in this particular in function f, when you're supposed to access Pn, you're not accessing Pn anymore. And it will cause a segmentation fault because the first parameter of main is an integer that is a relatively small number, typically 1 or 2. And you're going to dereference it as a pointer. So that dereference action will cause your program in this subroutine to crash right away. Now when it does crash, if you encounter a problem like that in your own homework assignment, what you need to do is not to just go, oh, the program just blew up, or I'm going to make some random changes to my program to hopefully fix that problem. Okay? Because that will typically make it even worse. What you should do is to go into GDB, stop, when it does crash, make sure that you know where it's crashing. In this case, it will crash in the subroutine in function f. So you know which instruction it's crashing on. Now, when it crashes on one particular instruction, you look at the operands and you say, okay, but which operand is responsible for the crash? And I can guarantee only one operand will crash it. Because in the Intel instruction set, you can only have one memory operand at a time. It is always the memory operand that can cause the problem. So once you identify which operand is causing the problem, the next thing you would see in this case is a base addressing mode. Okay? If it's base addressing mode, then what can cause the problem? Well, that's the displacement, okay? And there's also the register. Which one do you check first? I would check the register first, because in this case, the register is supposed to be a pointer to the structure itself. So you go ahead and use an IR and then EAX, EBX, whatever register you choose to do the dereferencing. And if that is 1 or 2, then you know what the problem is. Okay, it's not getting the parameter that you're supposed to. If it's not getting the parameter that you're supposed to, then you have to ask, why am I not getting the parameter? Okay, so you have to stop and then trace your way back in the debugger to try to find out why am I not getting the parameter that I'm supposed to. Okay, so after that, let's go ahead and just implement the subroutine. All right, so we are only supposed to call printf with the 2 parameters. The string thing, I'm not too worried. I'll deal with it later. So right now, I just want to push the buffer component or the buffer property or member of the structure pointed to by Pn. The way to do this is I have to move Pn EBP into a particular register. I just use EAX whenever possible. Okay. If I have to comment, this particular line, after this executes, EAX becomes Pn. Are there any questions about the comment of that previous line? EAX equals Pn. Does everybody see that that's exactly what it's going to do? It's just copying the parameter into EAX. Pn is a pointer to a struct node. So it means that EAX is now a pointer to a struct node. Now when you have a pointer pointing to a structure, it's always pointing to the very first, the lowest byte of the entire structure. That's not what I want to push on the stack in order to call printf. I'm supposed to push the member called buffer inside the structure onto the stack. So that means I have to dereference, but I also have to make sure that I'm not accessing everything or the beginning of the entire structure. I am only accessing one particular member of the entire structure. So the push instruction is going to be pushing the value of the member, not the address of the member. So that means, since it's called node, the symbol is usually just node underscore buffer in this case. But instead of using EBP as my base register, I'm using EAX as the base register because EAX is the one that is pointing to the beginning of a struct node. And then after that, I'll just do another push L. In this case, it's the format string. And I can define the format string before F colon. Now, it is also important here to define a format string before F colon, because if I define it after, the literal string content becomes instructions. It will be interpreted as instructions as we call function F, which is not good. So in this case, I use ask keys, not ask key. It has to end with a Z to automatically have a null terminator at the end. And then I can just copy whatever it is supposed to be, %s \n. Now that I have pushed both of those on the stack, call printf, and then add long $A to ESP to balance the stack, and we're done. So the tricky part about this one is what am I supposed to push on the stack as far as Pn points to buffer is concerned. Are there any questions? Yep.
So you don't need to explicitly deallocate your local variables?
That's correct, because that's what the move EBP to ESP is supposed to do.
Okay, so if they're declared at the top, it's okay, but if they're declared somewhere else, then you have to explicitly deallocate them.
Correct. The allocation, which is add L $lost local var ESP, that's the allocation of all of your local variables, if
I
any.
understand.
Yep. And then the last part, move EBP back to ESP, will deallocate everything that you use in the invocation, including anything that you forgot to deallocate right after the call. So it will clean up everything for you.
So if we don't have local variables, do we still need to?
No, as I said in the previous example, you can just ignore add L $last local var to ESP.
Okay.
But I always include that, just so that, I'm just reminding myself as well as you guys that if you do have local variables, that's the place to do the allocation. So are there any questions about this particular subroutine? Now, if you look at the correct version of the subroutine, then you have to ask, but what if I do it in an incorrect way? What would happen? And the best thing is you can go ahead and do it. Okay, just change the order of these two operands and see what happens. Okay, because once you have the right implementation, you can always mess it up, and then you say, okay, but what if I mess it up? What is this program or what is this subroutine is going to do in that case? All right. Any questions? Well, let me ask you one quick question then. What if at the exit point here, I somehow did not have this instruction, the one that is currently commented out? What if I forgot about that instruction altogether? What do you think would be the behavior of calling this subroutine?
You're in an unbalanced stack.
I have an unbalanced stack by the time I get to the return instruction. Okay, so the question now is this invocation of the subroutine going to crash, or can I make my way back to the caller and mess up the caller in the process? What do you think?
It's going to mess up the caller.
No, it's going to crash right here. Exactly, the return address is going to be incorrect because it's no longer. So instead of using the correct return address for the return instruction, I'm using the value of old EBP as the return address. So that would try to force me to return to another place on the stack, which is most likely, either one, I cannot execute instruction on the stack itself, or two, it is not a valid instruction. So most likely it's going to crash right when I execute the return instruction. So those are the kind of questions that you have to keep asking yourself is, what if I mess up here? What if I mess up there? What if I have, what if I miss that instruction? What do you think the program is going to do? In other words, I somehow forgot to restore the stack pointer from the frame pointer.
Yes.
So the stack pointer is still, doing things. In this particular case, nothing is going to happen.
As long as you've kept your stack balanced.
Yes.
If you haven't kept your stack balanced at this point, then it's just going to continue being problems.
Then it will use the wrong part to restore to EVP, and then it will attempt to do a return. Right.
And if you have local variables,
If lost local var is not 0, then the stack is guaranteed not to be balanced because of the lack of this instruction. And then the next instruction will not crash, it's the return that will crash because it's going to use the wrong part of the stack as a return point. Okay. So that is really the kind of thing that you have to keep thinking and say, okay, but what if I mess up this part and the other part and so on? All right, so that's the end of this particular one. Let's go to question number 3. So each one is really set up about the same way. And in this case, we are supposed to implement this particular instruction. It's a complex number type of calculation thing. This one does have multiplication involved. So let's go ahead and just do this one. It has there's one thing here that we have not talked about in this class. Has anyone noticed anything about the parameters that is a little bit unusual that we have not really talked about in this class? Where's the pointer? What is x exactly? Is x a pointer to a struct item, or is x itself a struct item? It is a structure. So this is passed by value. I'm passing the entire structure on the stack. And you can do that in C and C++. The only thing you cannot pass by value is an array, but the structure can be passed by value on the stack. Okay? But what does that mean? What is the implication when you pass an entire structure on the stack? It's just like a local variable, exactly. Okay? So let's go ahead and take a look at this code here and try to figure out how to implement it. So we'll go ahead and display the C code and also the assembly code side by side. And what is the name of the subroutine?
Main item? Or no, sorry.
Bolt item, I think. And there we go. There we go. All right. So this is what we want to implement, and this is the assembly code for that. Okay. Doesn't take that long to type this in, so I'm gonna type it in anyway. All right. What about x? Well, x is passed by value, and it is passed on the stack. So how should I define the displacement to find parameter x in this case? Is it any different from before? It's not any different in this case because it is right after the return address. So it is still return address plus 4 because return address itself has only 4 bytes. It is y that is tricky because it's no longer just x plus 4, because now we have to say it is item underscore size. It is the size of one item because we are passing item on the stack. So are we still doing okay in this case? Okay. So we have two structures passed by value on the stack. I have one local variable. So in this case we have answer. And answer is going to be allocated on the stack, which means it's going to be O EVP minus the size of one item. So we have just minus item size here. And in this case, if I had this code here, the template for the entry code and the exit code stored in the file, I can just copy and paste it because it works in all cases. So move ESP to EVP, and then add long last local var to ESP, and obviously I have to define that here too. Last local var is answer. And then the exit code is the opposite. Restore the stack pointer first. And then from there, we can restore old EVP, and then we can just do a return. All right, so the actual content of this particular subroutine starts here, where the cursor is. I have to do some calculations here. It looks really complicated, but it really is not, too bad. We can use the mul instruction, MULL. Let me just double check one thing first. I'm going to check u3.h. It is in32.t. So technically speaking, I have to use imul because that's the signed multiplication. So I'm going to use imul in here. Okay. We have to do the calculations here. I'm just going to finish one statement because the next statement is really about the same, so it's not really that challenging. Oh, there's one more thing that we have not talked about, so I cannot ask questions like this in this class. It's how do we return a structure? I'll go over that, but at the same time, I'm gonna, I won't ask that question because it's kind of last minute. Okay, so first of all, we'll do the calculations. X dot I times y dot r. All right, so to do multiplication, we have to set up certain registers. Can anyone still remember what is the implied operand of multiplication? EAX, okay? So EAX is one of the things being multiplied, and then the other one is the operand of the instruction itself. So that means if I want to do multiplication, one of these things have to be put into EAX first. So I have to put something into EAX. So let's say that I'm dealing with this multiplication. X dot I has to be put into EAX. Can I do this in one single instruction? And if so, how am I going to specify the first operand? But first of all, can I do this in one single instruction? The entire structure is on the stack. I need to access a certain portion of the structure. So we can do it, okay? All right. Now, because it is a part of the call frame, I can kind of guess that we'll use EVP as a starting point, but I don't need to go to where EVP points to. I need a certain displacement. Because we're using parameter x, I think the label x is going to be here as well. But we are not accessing the entire structure or the beginning of it, not necessarily. We just want member I, so now I have to specify the displacement to member I in a struct item. So we have item underscore I specified here. That is going to move member I, the value of member I into EAX. Are we still doing okay at this point?
Do we need parentheses around x plus item I?
No, you do not, and I think it may not have a problem with that if you have a pair of parentheses, but you don't need it. All right, so after this, we can specify the actual multiplication instruction. And as I said a little bit earlier, this is signed multiplication, so technically speaking, you have to use imul instead of mul itself. And the other one is y plus item underscore r EVP. I cannot remember whether this is a supported addressing mode. Can you use a memory operand next to mul? We can just assemble the file to find out. And then you can finish up the calculations. So the question now is, the next question, so let's say we have dot 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 here, and then we have the answer. The right-hand side is in EAX already. How do we store that into answer.i? It's pretty much the same thing, right? If the answer of the right-hand side is already in EAX, we just use a move L instruction. Move along EAX to, in this case, answer is a local variable. We want to store the answer into member I of that particular structure. So we have item underscore I. And because it is a local variable, we are still using EVP to access it. The dot 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 part is kind of boring, so I'm not going to finish that part. Any questions about this answer up to this point. Okay, so let me just put another dot here. Now we need to return the entire structure. So this is one thing that we have not talked about, and it's not simple. Then that's why I could not ask that question in this particular semester. How do we return an entire structure? Look at the return type of mole item. It is not returning a pointer to a structure, it is returning an entire structure. Well, as it turns out, what the C compiler does is if you're returning an entire structure, it won't fit into registers because you have no idea how big the structure is. So every time you return a structure, it is not returned by EAX. Instead, what the compiler does is it will actually insert a hidden parameter on the stack. Okay? So in this case, there's a hidden parameter on the stack right between return address and X. And the return, I would just call it return value address. Okay? So this one is actually getting return address +4, and then X is getting return value address +4. So we have one additional item that is not visible in the C version that is pushed on the stack.
How does it know that you're returning a structure if you write it currently?
Well, we'll take a look. Because from our perspective, we are looking at the C code, so we know that we're supposed to return an entire structure. The C compiler will set up the stack accordingly, thinking that it's calling another C subroutine that is placed by these rules. Okay, so when we write programs, in this case, when we write it in assembly, we have to follow exactly the same rules so that the caller can get the return value accordingly. Okay? From the perspective of the caller in this case will first push Y by value, then it will push X by value, and then it will push a pointer to a quote-unquote certain place to store the return value, which is an entire structure on the stack as well. Yep.
Is assembly built to interface with C, or is that kind of like hackish?
That's a good question. Okay, so if you remember last time we talked about Ritchie and Carnegie, the people who wrote C in the first place. They wrote C as a programming language because they were sick and tired of writing assembly programs all day long. And C was more or less like a macro language to begin with, so that they can simplify things like when they say X++, the compiler, or then it's just a macro processor, will generate the assembly code to increment a particular value by 1. Okay, so that's the origin of C and C, not C++, but C itself. So the answer is yes, it is actually designed to integrate tightly with assembly language programs. The way we use it these days, obviously, is not really quite the same way that those two guys used C and C++. Well, not C++. I kept saying C and C++, but back then it was only C, and it was actually the predecessor of C, which is called BCPL. Most people know it as before C programming language. I have no idea what it's supposed to be. Now I have to find out. Random curiosity is definitely distracting. So BCPL. Okay. Language. There we go. Basic combined programming language. There we go. So let's click there. It's no longer in common use. So it was actually the basis of the C programming language. And then if you look at who wrote it, Martin Richards from Cambridge. And this predates C because I think C was in 70 or 72. So this predates C. But most people look at BCPL as before C programming language, which actually makes sense too in this case. There you go. I just want to see whether it has like sample syntax and stuff like that. Well, there you go. Sample syntax. Doesn't look like C at all.
It's more
Well, it looks
basic.
more like C than assembly.
True.
More basic.
Let's. Yeah, the use of dollar signs.
Lots of capital letters.
Let try.
Yep, let.
Let's start.
And all right.
Pascal assignment statement of performance.
All right. So now that we know, how the stack is set up and what is the intention of return value address, that means at the very end of this subroutine, we have to copy the entire answer, which is a structure, to the place where we are supposed to return the value, of an entire structure. So that means, we have to copy what we know as the local variable answer to where, what is that again? Return value address points to. Okay. You can do it with your own loop. Okay, you can set up a loop and just copy it byte by byte until that many bytes are copied, or you can just call memcopy. I'm lazy. I just call memcopy. So I just want to give you the entire answer to this particular question. So let's go ahead and memcopy. Memcopy has destination, source, and then a number of bytes to copy. So that's what I'll do here. So I'll push the number of bytes to copy first because that's the third parameter. So it starts with a push L. In this case, it's a item underscore size with dollar sign. So that makes a very good. This makes a very good component in the final exam. Is occasionally I might forget to put a dollar sign where one is expected, or I put a dollar sign when one is not expected. Okay, so this one is particularly nasty because with or without a dollar sign, they're both valid operands, but the meaning is completely different, right? So you have to understand what the dollar sign really does to an operand in order to spot these problems. Okay, so this is the third parameter. I think the second one is the source where I'm copying from. So now I have to push the address of answer itself. I cannot do that with one single push because in this case, it is the address of a local variable. So there are two things. I can do it, in different ways. One way to do it is to push EVP itself on the stack, and then I can add the displacement to local variable answer, to whatever I just push on the stack, ESP, like that. So that's one way to do it. And then last, I have to push the address of the destination. But that part is actually easier because it is, a certain thing on the stack already set up. So in this case, it is my return value address from the perspective of EVP. Once I push these three components on the stack, I can call memcopy, memcpy. When memcopy returns, I should reclaim those 12 bytes on the stack by doing this instruction, adding 12 back to the stack pointer to reclaim those bytes. So that's how you return an entire structure from a C subroutine. Yep.
Is memcopy a C?
Yes. Memcopy is defined in libc, which is automatically linked with when you go through GCC for linking purposes. So that stuff is already automatically linked, and so you might think that if my program is not using memcopy, isn't that going to be wasting space because it will just link with printf, memcopy, and all those other things? The answer is no. The linker is actually pretty smart. It will only link and include the code that is actually referred to by somewhere in your program. So that's why if you're not using memcopy, it's not going to copy it. And memcopy is actually a very short subroutine because its only job is to copy from this many bytes from the source location to the destination location. All right. So once again, I'm not going to ask anything about returning an entire structure because this is the first time we see it, and you guys didn't have a chance to really play with this sort of thing. So I'm not going to ask any questions for that. All right. So let's go ahead and move on to question number 4. So main.c and so uppercase O to be side by side. There we go. So this time we have something that looks like this. How would you implement something like that? Okay, first of all, we want to understand what that line is actually doing. Okay, because it has 2 dereferences and 1 post increment. Okay, so you got to figure out the order of operation. Well, since I give you parentheses to clarify the order, it's not as difficult anymore. If I did not give you the parentheses, it's a little bit harder because then you have to remember the priority of operators. Okay, am I dereferencing first, or am I post incrementing first? In this case, there's no question because the parentheses clearly indicate that we are doing 1 dereference, post increment, and then another dereference to store the result.
You couldn't do that one without the parentheses, though.
Huh?
You couldn't do that one without the parentheses, though, because the
post increment is taking precedence. Yep.
and well, that and even if the dereference symbol took precedence, it would dereference both times before it would hit the post increment. So there's no way you could get that same effect without the parentheses.
Yep. But even if there was, I would always use parentheses just so that everybody understands clearly which one goes first. Because this class is not about, how much can you memorize about operator precedence in C. It's about, okay, these are the individual operators in C. How do we implement these things in assembly? That really is what I'm testing. All right. So let's go ahead and do this one. I'm skipping the definitions of the parameters and stuff like that because it's really kind of generic. So I'll just go ahead and start with the subroutine itself. Push EBP, move ESP to EBP, and add L last local var, which is definitely optional because we do not have any local variables in this case. And then do the reverse. Now there's one potential danger of doing it like this in my class, is people keep doing the same thing but not remember why we have move ESP to EBP or why we are pushing EBP at the beginning. So so you still have to kind of remember why we are doing that. All right, so now we are down here, and assuming PPI is defined correctly as a parameter, how am I going to do that? Well, first of all, PPI itself is a pointer to a 64-bit integer. So we have to deal with that first. So the first thing we have to do is we are not interested in PPI itself. We're interested in what PPI points to, right? So that means you have to move PPI EBP to a register first because I cannot dereference using a single instruction like that. Okay, so the first operand in this case is whatever PPI points to. In other words, I have just done one particular dereference. All right. So the next question is, what am I going to do here? I have done the first dereference. I'm supposed to do what is the next thing I'm supposed to do?
Post increment.
A post increment, exactly. Okay. Now, how do you do a post increment in assembly? There are several ways to do it. Okay. With a post increment, you are actually doing the increment, but in order to utilize the expression, you're using the value before the increment. So I do want to increment the pointer that is pointed to by PPI, but I want to use the value before the increment to do the last dereference. So there are several ways to do this. Since we have the stack, it comes in very handy. Okay, so I'm just going to save whatever PPI points to before the increment. So later on, I can just push, I can pop it, and use that particular, pointer. And after this, after I save it, it is now, saved to do the increment. To do the increment, this is a 64-bit. PPI is a pointer to a 64-bit integer. So now the question is, okay, let me just ask you this here. I know I'm supposed to add something to whatever EAX points to, because I'm supposed to increment whatever it points to. The question now is, what is the question mark? Am I incrementing by 4, or am I incrementing by 8?
It's still 4 because we're in a 32-bit operating system.
Well, the parameter specifies that PPI is a pointer to a 64-bit integer. So it is a 64-bit integer at the very end. The question is, am I incrementing a pointer to a 64-bit integer, or am I incrementing a pointer to a 64-bit integer? Well, it's a pointer, but what is it a pointer to a 64-bit integer, or is it a pointer to a pointer? It's a pointer to a 64-bit integer. So to increment a pointer to a 64-bit integer, this has to increment by 8. Okay, is that all right so far? Okay. Now that the increment part is done, I can try to finish up the storing of the 0. Okay, so that means whatever I push on the stack, now it comes in handy. I can pop it back, into a register. I pop it into EAX. Yep.
If we're only if we're still going to be adding 8 to adjust that pointer, then why wouldn't we be using 64-bit registers?
64-bit registers.
Like RSP, RBP instead of EBP. Because EBPs are 30.
But this is a 32-bit architecture, so we
Right,
don't
so
have.
aren't all pointers still 32 bits?
All pointers are 32-bit, but we are incrementing a pointer that is pointing to a 64-bit integer. And that's why when you're adjusting the value, when you're adjusting the address, you're adjusting by 8 because the size of every item that it points to has 8 bytes. Okay. I'm trying to figure out what to do to clarify that. Okay, let me just do this here.
So we're assuming that everything around it is also 64-bit integer.
Even if the object itself is 64 bits, I would have expected the address of it to be 32 bits.
The address is 32
The address
bits.
is 32 bits.
So that's why it makes no sense.
We're
Okay.
changing the address.
You add to a pointer, it doesn't, like if you have a pointer to
It's like you have an array of
64-bit integers.
The question that's in my mind is not going to be answered like that.
So are we doing okay so far, or do you want to go through this one? It's a simplification of what we're dealing with right now because it doesn't have a pointer to a pointer. It's just a single pointer to a 64-bit integer. So to implement this in assembly, what you need to do is to say, this is a pre-increment too, which makes it a lot easier too. So to implement this, you have to move PTR, EBP to a register because we eventually have to do a dereference. But because it is a pre-increment, we have to add first. Now, when PTR in this case is a pointer to a 64-bit integer, so everything that it points to is supposed to have 8 bytes. It's 8 bytes long. So when you increment, it is actually, you're adding 8 to the address, not adding 1 to the address. So that's why when we have to add, we're adding 8 to EAX because EAX is the pointer right now. Then we can do the dereference in this case. So we can now say, move L 0 to whatever EAX points to. And we have another move L to the other 4 bytes, because every time we do a move L, we are only moving 4 bytes, but whatever EAX points to has 8 bytes. So we have to separate the writing to the 8 bytes into 2 different steps, because we lack a single instruction that can write 8 bytes at a time. Are we doing okay so far with this kind of simplified example? Now that this one is done, we can go back to the other one and try to finish it. All right, so maybe I should change this a little bit, and yep, go ahead.
Could you go back and explain that?
The other one? This one?
Yeah.
Okay, sure. Okay, so if I use comments to explain it, EAX in this case is PTR after this instruction. And in this case, we have EAX is PTR plus 1. Actually, I forgot one thing. I'm supposed to store that back into PTR, so I really should be doing this too. PTR. So that part is basically saying PTR is EAX. This is hard to explain in C syntax because in C syntax, this is kind of like star PTR is 0, but it only affects the least significant 32-bit. Okay, so let's just say, but only for the least significant 32 bits. And then the other one is finishing the other one. This one is for the most significant 32 bits. Is that okay? Storing back into PTR is not necessary because I'm not referring to PTR afterwards. But to make this code truly equivalent to the C code, I should be doing that. Throughout all this code, EAX is a pointer to a 64-bit integer, right? Because after the first instruction, I never changed PTR except to increment. This is the instruction that makes EAX a pointer, right? The second instruction is really, the second and third instruction is just to increment the pointer itself. But since PTR is pointing to an 8-byte thing, when I adjust the address, I have to adjust by 8. To actually store something starts with this instruction. But since this is a 32-bit instruction, I can only affect 32-bit at a time. So I have to break up the two write operations into two instructions. The first one to deal with the least significant 32-bit, and then the second one to deal with the most significant 32-bit.
Okay, I have two questions. Also, to get it, maybe you could dereference EAX first and then do the add L4 to EAX the second most significant bit. So dereference EAX,
Right.
then put 0 in EAX, and then add 4 to EAX, which is anything interesting.
Yeah, we can do that too.
I just in case you didn't get it.
Right. Because we don't have to save the value of EAX, so we can add 4 and then do another dereference. But effectively, it's the same thing as a base register. Right. So now let's go back to this code here. And I'll do the same thing, I'll use comments to basically indicate what each EAX is. So in this case, it's pretty clear that EAX is just PPI. And we are saving what PPI points to on the stack with this instruction. And then this is incrementing whatever PPI points to. So I'm increment whatever PPI points to. PPI points to a pointer. No, PPI is a pointer to a 64-bit integer. So might have made a mistake here. Yep. This should be 4. I was wrong because what I'm incrementing is still a pointer. Nope. It's not a pointer to a pointer anymore. It's just a pointer to an integer. So I'm incrementing this. So that's correct. Okay, that is okay. Because I am incrementing whatever PPI points to, and that is a pointer to a 64-bit integer. To increment a pointer to a 64-bit integer, I have to add 8 to it. Okay. So with this one here, EAX is whatever PPI points to. because that's what I saved earlier on the stack. And then the rest is just to actually store the result. So I have move L, a 0 into whatever EAX points to. So this becomes percent PPI is 0 for the least significant 32-bit. And then the next one is going to be another 0, but 4 bytes offset to PPI dereference twice for the most significant 32-bit. There we go. Good.
So what are the pointers, 64 bits?
The pointer is not. Whatever the pointer points to is 64.
So what
So
if you add 8 to the pointer PPI?
Okay, let's draw a picture, and I think that will help.
Just even the in-between points that you could have a point.
Okay. Oh, you know what? You guys need to fill in these forms, because otherwise, people will complain and say, "Tag, you never let your students specify or tell us whether they learned what they're supposed to learn." And that's okay. If you don't get this stuff, don't worry. None of the questions here ask anything about, incrementing a pointer to a pointer. Okay. So the final name. All right. So let's go ahead and use some low tech here. But it's a microcomputer. That's a good one. Thank you. That really tells you, how old this class is.
Yeah.
Yeah. Why is programming a microcomputer any different from programming a computer in general?
We didn't do anything with DOS.
Huh.
You get the rest of those through every decimal bits.
What?
Oh, yeah, we passed it back that way. Thought you had something.
Okay. Wait, there's more than one page?
No.
It's
It's only one
just-
page.
These guys
We
are.
get like,
No, but it's up here.
All right.
choices, huh?
This is a very,
Looking around.
very strange.
Okay.
This is dated.
Well, I guess you guys are all kind of focused right now, so I'm gonna use this time to draw some pictures.
Thank you.
Okay. So we have the PPI itself. It is a pointer. And this pen is not working. So a pointer. 64-bit.
We didn't do anything in DOS, so I can't.
Yeah, there's the same question, 1.3 and 1.6. Well,
That's not very efficient.
BCD. That's the read.
BCD stands for binary coded decimal. Now you know.
Strongly agree.
It is it's a very archaic way to represent numbers.
It's important to know for storing real numbers. It's important to know for storing real numbers.
No, we use floating point numbers to represent real
How the
numbers.
floating point is stored in
Huh?
the floating point, how it's stored in memory.
Nope, floating point is not like that. Yeah, BCD is only used for banks. Where you have to represent, like I think up to a tenth of a cent exactly, because there's no way to represent a tenth of a cent exactly, unless you use either BCD or fixed point calculation.
Yeah.
And to a bank, it is
By the
important.
standards of when microcomputer was coined as a term that was like more powerful than that could have been made.
Yeah.
Solve complex problems.
Hmm?
I'll disagree with that one.
Just to focus.
Maybe it's a simple problem that we can't solve.
And the interesting thing is I only get a performance evaluation in the fall. So this class is never evaluated for that purpose.
I don't have a thin film tip. What is this thin film tip nonsense? Oh, here we go.
It was different than
Okay.
BCG.
That's not very good at all.
So are we done with the evaluation? I mean, there were only, what, 5 questions on it?
6.
Difficult
6?
questions.
Difficult questions.
There's things I've never heard of.
Apparently you didn't learn it.
Yeah, you can tell from the questionnaire, how dated the curriculum itself is, because this is actually coming from the curriculum itself, and that's why they ask these questions. They should have, included in here. They should have said, or a more modern concept that replaces this. Okay, I think that's the best way to do it.
Yeah, I agree.
Do you strongly agree?
I very
DOS.
strongly-
1 out of 5.
I don't know. I couldn't answer none.
5 it.
Five it.
So it was 4.
Sorry?
Yep, there it is.
Well, let's take a look. Okay, so let me also copy the instruction that we are trying to implement. Okay, so the instruction we're trying to implement is asterisk, asterisk, PTR, or PPI, plus equals to 0. Okay. All right, so getting back to this code here, so let's try to figure this one out. Okay. So the first one, which is the internal dereference, this part here will get us here, right? Because it is a dereference, so instead of accessing a pointer to a 64-bit integer, we are now getting to a pointer to a 64-bit integer. But the post increment is done to this guy.
So what are you highlighting right now?
Right, that's what the post increment is supposed to do. Right? Now, so that's why we are incrementing now a pointer to a 64-bit integer, right? So that means if I have another 64-bit integer next to this one, this guy now needs to point here. The pointer has to be modified to point there. And that's why the addition is added, that's why I'm adding by 8 instead of adding by 4. Okay? And so if you follow the assembly instruction, this one here is done by this instruction. We are saving this one here. And this is what we are saving on the stack. The pointer to this location is what we are saving on the stack. So later on, after we pop it from the stack, we just have to say, oh, you know what? This part here has to be zeroed, and this part also has to be zeroed, except this part is just 4 bytes off from where EAX points to, and that's why a based operand will do the trick. Yep, go ahead.
Could you go back to the code? I have a question.
All right. Sure.
Yeah, so when you, let's see, right there, when you push long EAX, you dereferenced it.
Yep.
And then when you added 8, you referenced EAX the second time?
Because EAX at that point is still pointing to the pointer that I'm supposed to change. Okay. So you're asking, okay, let me go here first and turn on my numbers. No, that's correct. There we go. So you're talking about which line?
Line 9 and 10.
Line 9 and 10. Okay. So what we'll do is we'll look at this picture, step by step. Okay. And I'll just label everything as line 8. So after line 8 executes, EAX will point to the very same place that PPI points to. Is that okay so far? So 8 : means after line 8, EAX is pointing to that place. Is that okay? So if you look at line 9, what are we pushing on the stack? We are not pushing the pointer itself on the stack. We're pushing this thing on the stack. what is this thing pointing to? It's pointing to the 64-bit integer. So the stack now contains, if you look at the stack, because the stack always grows down, this is the stack. Oh, you cannot see that part. Okay, there we go. Okay, so we always push down on the stack. So after the push instruction, so after instruction 9, which is push L, whatever EAX points to, what we're pushing on the stack is the pointer that points to the 64-bit integer. Is that okay? That's the effect after line 9. And then line 10 is adding 8 to whatever EAX points to. EAX is still pointing to the same thing here. So that means, after line 10, EAX is no longer pointing here, but it is pointing to, we're adding 8 to whatever EAX points to. So EAX is pointing here. Okay, so EAX itself is not adjusted. So after line 10, I have to, okay, this is the way to do it. So after line 10, EAX points here. So this is after line 10 of adding 8 to whatever EAX points to. I'm not adding 8 to EAX itself, I'm adding 8 to whatever EAX points to. But are we still doing okay? I know the picture looks kind of cluttered at this point. Yep.
Would it just be EAX, not EAX in parentheses?
No, I want to increment whatever PPI points to, but at this point, EAX is the same as PPI. So that's why I have to add 8 to whatever EAX points to, because I want to add 8 to whatever PPI points to. And then line 11 is going to pop whatever the stack has into EAX. So at the end of line 11, EAX points to whatever the stack item points to. The stack item is still pointing to this location, right? So that's after line 11. And then lines 12 and 14 is just going to change whatever EAX points to, all 8 bytes of that to zeros. So that's why these 8 bytes will now get zeros. So the assembly code implementation is correct if you follow it step by step. It's just kind of messy because we have all those operators, dereference, post increment, and then another dereference. You just have to do it in the right order. So as a hint, bring extra pieces of paper in the final exam because you might need to draw pictures. Or you can just take a screenshot of this and then bring the printout with you. I think that really is the best thing about screen recording is you can just freeze the frame, print it out, and put it onto your pile of paper that you want to print. All right, so
I think you should offer downloads for your video files.
Downloads?
Yeah.
You can download from YouTube.
There's a couple
You
of
can. You need a separate program to do that.
You can get a Flash God, which is a plugin
I have a program that
installed
can
in
do it.
Firefox. Yeah, you can just download it, in the highest, possible resolution or lower resolution, whatever you want to do.
I feel it'd be, I don't know. But it's useful to be able to play it in your own media player because YouTube doesn't have smooth scrolling through the video.
It does not?
No.
I thought it does.
Just download. I have all the videos downloaded. Like,
I know.
you really want.
Okay, but as the last step of this class, I'm going to zip everything, that I have, ever worked on for this entire semester, and then upload that too. So
For a while, I was typing.
If YouTube feels like it, it will scroll somewhat smoothly through the video, but only if it feels like it.
all right, so this is the command to do it.
It's mood. It's got its moods,
Frame.
I swear, it's so more exciting.
There you go. One more ball.
Whoa, that was insane.
All right.
Can I just get that on a flash drive because my internet's
Yeah.
No, I'm putting this like a doodle.
I know, but while we're here.
Oh, I don't feel like
No.
doing this today.
No, I'm not gonna do
I
that.
estimate how much my internet was.
Over there?
Okay, that file is 444K. I hope your flash drive has enough space to store it.
It does.
Oh, you want to skip through this part of the video? I hope you're all right with me taking 5 minutes to catch up on everything else. I just don't feel like. What? Yes. Oh, thank you.
See you out, man.
Here's a bunch of spares.
Doesn't matter, you know, the machine can scan it in any direction, any orientation, you know, face up, face down. Yeah.
Those are spares.
Oh, let the machine scan it too. I don't care.
I know, but I prefer to handle them. I'm like, no, you're not. It's easy.
No, all you do, that's in your manual you're testing. And all you gotta do is just make sure you catch it.
Okay.
He got mad at me for doing anything other than just throwing. Don't look at my code for that.
You guys. You know, Tack, it's somewhat fun learning. It's somewhat fun learning all this assembly code, but I'm gonna stick with other languages at a higher level.
But there's so much things.
Tag, what are we doing on Thursday?
On Thursday?
Yeah.
Nothing.
But all the
We
This
don't
is the
have
last
class on
lecture.
Thursday.
Also Thursday, then no
Thursday is the first day of the final exam.
Things you're like, why did I do this?
So this is the very last lecture. There won't be any labs or lecture anymore after this one.
So there's no labs on Thursday either?
No labs on Thursday.
Oh man.
You guys didn't know that.
I want to ask you a question about the adding of last local var to ESP. So there's a local variable declared within a subroutine. So we have to allocate this thing. We have to add. Or what's the purpose of this?
It's to reserve space on the stack so that other subroutines and calls don't mess with our local variables on the stack. When you